Hi, this is our second video on the normal distribution, Module 3, Video 3, I'll call it 3B. I think I'm still going to have to break this into two because this is a long section and we talk about standardizing the normal random variable. Before we get there, he just had one more example of working with a normal distribution. So imagine you have these shafts. Shafts manufactured for use in storage devices. They have diameters, so I'm going to let diameters be my random variable x, and those diameters are normally distributed, so I know x has the shape of a normal, and we're told what the mean is, so 0.652. Specifications state that shafts have a length in this interval, so I want all shafts, 90% of them over here, it says 90% to be in that interval. And the thing I'm looking for then is what standard deviation do these diameters need to have such that 90% will fit between these two values. So right now I don't know what the standard deviation is, so I'll put sigma squared there for the variance. So this is just working with a normal curve again, and I'm not going to find the value in maple. I think if I set it up, that should be good. So I want the distance between these two values, or I want the area between these two values to be 90. So, or 0.9, sorry. So 0.647, I'm subtracting from 0.652 and 0.657. I want the area under the normal curve to be 0.9, and since I don't know what sigma is, I'm just going to write times sigma times e to the negative x minus 0.652, 2 squared divided by 2 times sigma squared. So I would just put this into maple. This becomes a maple problem and not a statistics. If you can set this up, I feel good that you'll be able to solve it in maple. And if you forgot, just ask me, or send an email or ask me to do a maple problem in class. It's no problem. So I'm leaving that as is. Down here, we're talking about a standard normal random variable. So a standard normal is really the easiest to work with normal curve. We reserve a special random variable letter z for it. So z is a normal random variable where the mean is 0 and the variance is 1. So these are the easiest possible parameters I could put in to simplify f of x. So a lot of times we're going to convert any normal random variable to a z just because he's easier to think about and work with. So we have a problem here where we have the driving distance in golf for men and for women. So let's just call it M. Here's a drive distance for men off a tee in golf. The drives are normally distributed with a mean of 260 and a standard deviation of 15. And let's call the random variable W the women's drive, which is normal with with a mean of 254 and a standard deviation of 18. Let me see, I didn't make up anything, so this would be 260 and 15. For females, it's 220 with a standard deviation of 18. Sorry about that. So this guy has a mean of 220 with a standard deviation of 18. Sorry, I've already done, I don't want to go back and do it again, so I hope this makes sense to you. So there are two different distributions, and to compare her total amount of yards, 254, in comparison with other women, and his 280 in comparison with other men, we're trying to find out with respect to their gender, which is really driving farther with their group of people. And I mean, obviously 280 is further than 254, but with respect to the distribution they're in, 254 might be further in the tail of the women's than 280 is in the men's distribution. So I guess what I'm trying to say is, if you look at this distribution that's at 260, how far in the tail is, over here somewhere, is how far he can drive the ball at 280, but does she actually have a better overall distance with respect to women? Here's their mean at 220, but she's out here at 254. So what we're trying to determine is who is further out in the tail according to their distribution. So what I can do is standardize these values. So we actually call these z-scores. So z, I'm going to put z for men, or for Zach in general, is his drive is 280. So I take the value x, I subtract off the mean of that distribution, 260, divide by 15, and I get 1.33. And for the women, I do the same, or let's put W there. I do the same thing. I take her distance, which is 254. I subtract off the mean for women, divide by standard deviation, and this comes out to be 1.89. So she's further out in the tail of her distribution, meaning that there's fewer people that have better drives than her. And over here, there's more guys right to the right of him having better drives. So overall, with respect to gender, she is the better driver. And I kind of even drew the picture. Like here, this is probably more than 1.33, maybe 1.33 is about there, and over here 1.89 is closer to 2, so you can see there's less area in the tail for her distribution and score than his. So that's the main reason of that section is to talk about standardization. And so in order to classify like an extreme value, we kind of need a point to center on. So I'm going to say we consider the center of a distribution and its variability. And if we know these things, we can put them all in put values in the same unit so we can do comparison. So a z-score is really just the number of standard deviations that a value is in the tail away from the mean. So a z-score, as you saw I did up there, if you have the x value that you're interested in, you subtract off the mean of the distribution and the standard deviation, divide by standard deviation, you get a z-score. And this is unitless, but it allows you to compare scores coming from different distributions. So it's a very nice, well, we do that a lot in this course. So back to, they said address the question about the driving distance, and we already decided that hers is a further distribution with respect to her gender. So this is just saying we're not always going to have, right, a normal 0, 1. So here we have a random variable x that's normal with mean, mu, variance, sigma squared. What if we took that random variable and we multiplied it by a constant, so ax, where a is the constant, and then added b to it. So all I'm doing here is a linear transformation of a random variable. I'm multiplying it by a, so maybe I'm stretching or shrinking it by a constant, and then I'm moving it, right? I might be moving it left or right. That's all I'm doing to the distribution. And so we want to figure out a way to standardize any distribution. It would be nice to know what the mean and variance is of this new random variable. So if expected value of y should be the expected value of, is the expected value of ax plus b. But remember, the definition of expected value is just an integral, and we're allowed to pull constants in front of integrals. So this is expected value of x. And then over here, expected value of b is just a constant, so I expect b to be b, and I'm allowed, right, if I had an integral, I could break up into 2 pieces, so that's legal, and this is just going to turn out to be b. So right now, I know y, if x was normal, then y is definitely going to be normal, because all I'm doing is shifting it. The mean will be a times expected value of x plus b, and now I want to find the variance, so the variance of y is equal to the variance of ax plus b. Now when we found variance, remember there was an integral, but we had a squared term in there. So this doesn't actually come out as a constant, it's going to come out as a squared constant. So a squared times the variance of x. And then the variance of b, b is a constant, it doesn't vary, so that's just going to be 0. So y is going to be normal, this is the mean, and the variance is going to be a squared, so a squared times the variance of x. Okay, so all I did was a transformation, and I'm finding the new mean and variance. So over here, they're standardizing a random variable. So we started out with x, who's normal, with a mean of 3 and a variance of 4. And then what we're going to do is subtract 3 and divide by 2 and see what we get. So here's the distribution right now. It's sitting at 3 with a standard deviation of 2. Okay, so now I'm going to standardize it. If I subtract 3 from this random variable, I'm shifting it 3 to the left. So now this random variable is going to be centered at 0. And then what I'm going to do by dividing by 2, right, I'm actually changing the stretch of this curve. By dividing by 2, I'm going to make it actually a little bit tighter, right? So it should look like that. So my random variable z actually turns out to be normal with a mean of 0 and a standard deviation of 1. So, and we're just using, actually we're using the definition we used in the last section of standardizing, right? Subtract off the mean, divide by the standard deviation, you should get back to a normal 0, 1. So let me see if there's anything else in this section, another example, or if I can, yeah, I think I'm going to just finish saying this and then we'll just do our last one. Standard normal, if blank, then we say z follows the standard normal distribution. Oh, if our original distribution is normal, if x is normal, then when we standardize it, we still get a normal. Z has standard units, the number of standard deviations from the mean, and it recodes each interval in the population by how far it is in the tail, or how extreme, how far, I'd say how far it is in the tail, by how far it is in the tail of the distribution. And standardizing a population only results in a standard normal, yeah, if the initial population is normal. I'm trying to wonder now, did he mean something? So standard normal, if x is standard normal, I don't know, if x has mean 0 and standard deviation 1, then we say it's a normal 0, 1. I'm not really sure what he wants there, but yeah, if x has mean 0 and standard deviation 1, we say it's z and it follows a standard normal. So anyway, I'm going to end this video now. If you heard, my dog was walking, the big dog was walking around, so anyway, I think 12 is, I'm trying to get down to 8, but it looks like 12 a lot. So anyway, one more I'm going to do probability distribution plots, but that's almost a totally different subject.